Okay, welcome. This is the week 9 webinar. We're getting close to the end. I don't know if you've realized that, but tomorrow's June and we go to almost, late June. So we're definitely, light is at the end of the tunnel. And today is today that we're going to do something that we haven't done yet in terms of the type of survey questions or variables that we've dealt with. Today is a completely new type. So, but really important, comes up a lot of times. And so let me share my desktop and I will talk about the things we're going to do today. So let me do that. Okay, so the plan today is, as always, I'll take questions and feel free to pop in the chat box or ask or whatever makes you most comfortable. Any question you have as we go on. And then after that, we're going to get into the chi-squared distribution. So in the past, we have looked at the binomial distribution, the uniform distribution, the normal distribution, the student's t-distribution. And today we're going to go to a new distribution called the chi-squared distribution. And just to let you know, chi is a Greek letter. So mathematicians like Greek for some reason. I have no idea why, but maybe because there are some great Greek mathematicians that did a lot of math. So they use a lot of Greek letters. Don't get mad at me if you don't like Greek, but we're dealing with it. And in fact, the Greek letter, it kind of looks like an X, except it's kind of a curly X. And you pronounce it chi. C-H-I is chi. And then squared, because the mathematics behind it, which we're not going to do the mathematics because it's too brutal, has a square in it. So we're going to be looking at the chi-squared distribution. Okay, then we're going to use the chi-squared distribution to do hypothesis tests. Because remember, the last half of the whole course is all about hypothesis testing. So we're going to be looking at something called the goodness of fit test. And just to let you know, these tests can handle variables that we haven't dealt with yet. And those are the qualitative variables that aren't necessarily the yes/no kind of variable. Things like, what is your favorite color? Okay, you're not going to say 34. You're not going to say yes. You might say purple. Okay, you might say red. And when you have several different possible words that can be spoken as your answer that have nothing to do with numbers, then we're talking about qualitative non-yes/no variables. And this week is the week of that. So pretty important stuff. Besides favorite color, because, who really cares about favorite color? Very important things. What are some other real important qualitative variables that happen in the real world?
Like ranking?
Ranking, well, ranking is quantitative, right? What's your rank, first, second, third, or fourth? That would be quantitative. There are a lot of good qualitative ones, I promise.
Like whether you're Republican or Democrat?
Yeah, let me go even broader, because Republican, Democrat can be done as yes, no. But how about what is your political party? And that might be Republican, it might be Democrat, it might be Green, it might be independent. So all those are words. Does that make sense? So that would definitely one is your political party. Another one might be, what is your race or ethnicity? Again, you're not going to say 33. You're not going to say yes. You're going to say, I'm Hispanic, or I'm Caucasian, or I'm Asian, or, whatever it might be, but it's a word that comes out. Does that make sense?
Education level?
Yeah, education level. So that would be something like, what is your education level? High school diploma, went to college but didn't finish, college diploma, master's degree, PhD degree, things like that. That would definitely be a qualitative variable. There are many, many, many examples. Others might be, what state were you born in? Okay, or what country were you born in? Okay, also nothing to do with a number. It's not yes or no. So that would be a qualitative variable. There's many, many, many ones. What is your major in college? That's also a qualitative variable, right? You don't say, I'm a 23. I was a math major. I'm not sure about your majors, but I was math, and very much not a number answer, even though math sounds like number. It's a word. Okay, so we're going to deal with qualitative variables, and we're going to be looking at the goodness of fit test. And the goodness of fit test is a test to see if the data fits the expected distribution. So that might be something like, do you think GPA has, or do you think major has anything to do with your astrological sign?
Yes.
Okay, maybe yes, maybe no. That's also, those are both qualitative variables. So you could look at something like, look at those who are the STEM majors versus the non-STEM majors, and to see if you knew about STEM, if you knew about everyone, but you want to find a STEM majors are the same as everyone, that would be a goodness of fit test, it turns out. Then there's tests for independence, and that's to show, is there a relationship or an independence or dependency relationship between two qualitative variables? So that means, does the type of car you have anything to do with the family situation you grew up in? You know, single mother, single father, married couple, some other thing, you know, etc. And the type of car might be a sedan versus a truck versus, you know, whatever. And you can find out, are those independent or are those dependent with each other? If you know one, does that give you information about the other, or are they completely independent? And then finally, we're going to be looking at tests for homogeneity. And that's something like, you have two different groups, and you want to find out if those groups are similar. So that might be, let's look at male versus female. Okay. And the question is the distribution of majors the same for men and women? Or maybe not. Does that make sense? Okay, I would guess that there's a difference. Again, until I looked at data, I couldn't tell. Any questions on that? So those are the chi-square tests. Question?
No.
Okay. So I want to open up to any questions. I want to remind you, I know you still have a few weeks before the project is due, but you should be, you know, working at your project. You should definitely have posted your project idea on the board, on the project 2 discussion board, and post any questions you have about it. I'm always happy to, you know, do my best to answer and help you out. And again, the main reason why I want you to post instead of email is that if you post, then you see the conversation and other people can see the conversation and get ideas of what works and doesn't work. So that's why it's more of a community kind of learning instead of just a one-on-one thing, which is much harder to learn. So that's why I have the post idea. But if you have questions about the project, this is a good time to ask.
I have some questions about the project, but also about lower bound and upper bound. That's the first one. It's like when either bounds go negative, I didn't fully understand like what it actually means.
Okay, so you're talking about confidence intervals?
Yep. Mm-hmm.
Okay, just want to double check that that's what you meant. Okay, so if you haven't, so I think the easiest is talk an example. If I talk in theory, you won't understand what I'm talking about. Let's do an example. Let's suppose you wanted to find out confidence interval for the difference between, how about GPA for men and women? Okay, female and male GPAs, just making something up. And let's suppose you found out your 95% confidence interval went from negative 0.4 to positive 0.6.
Okay.
For men and women, men being first, women being second in your list. Got it?
Okay.
So remember that you're taking a male minus female, right?
Oh.
So if male minus female is negative, what does that tell you about male and female?
that sometimes men have higher GPAs and some
Right,
like,
but what if it's, we're gonna look at this as a negative number, the negative 0.4.
Mhm.
So because it's negative, what does that tell you?
that it's higher than the
Which is
female,
higher?
the male GPA.
Yeah, so yeah, because it's male minus female, then it means that if you have a negative, it's actually the female that'd be higher.
Okay,
Because the second number is higher if you get a negative number. Do you see that? When you
Okay.
subtract.
I
So
gotcha.
that would mean that the female GPA, the population mean female GPA, would be no more than 0.4 higher than the male GPA.
okay,
Now the positive 0.6, that would mean that male minus female is positive. And that would mean that male is bigger than female. Do you see that?
Mhm.
So then you can say with 95% confidence that the male GPA is no more than 0.6 higher than the female GPA.
I see. So are you saying that if we're using a less than sign, then a negative number on the lower bound would be like a positive?
Okay, so first thing is confidence intervals don't have a less than sign,
Oh my
right? Only hypothesis
God.
tests
Okay.
do, right?
Okay.
So confidence intervals are they're just a confidence interval. They're left and right bounds. That's all they are,
Okay.
lower and upper bounds.
Okay. Okay. Sorry.
What matters is who you're writing first in your when you type out into the computer program, whatever.
Mhm.
If you're writing males first and then females, then it's male minus female. If
Okay.
you're writing females first, then males, that is female minus male.
Okay.
Okay, and that's always true. It's always, at least the way I programmed it, and that's pretty standard. Is it's first minus second.
Okay. I have another question for project 2.
Sure.
And it says the statistics for the difference if you're conducting a paired study that we have to summarize in. When you say which statistics for the difference, are you just talking about the confidence interval and the hypothesis test and I think
okay, so definitely the confidence interval and the hypothesis, those are the main parts of the paper.
Okay.
Okay. But there is one main statistic that you really have to look at.
Oh, the standard error.
And that is a standard error for the difference. Not the individual standard errors, but the standard error for the difference. That's the one that matters.
Okay, and that's the other question I had. I put it on the post. How do you find a sampling distribution if our data set is only 30 points?
Well, 31, hopefully, right?
31, 31.
So sampling distribution, if it's 31, is approximately normal. That's the first thing, because that's the central limit theorem.
I know, but
and then if you want the standard error is the standard deviation of the sampling distribution. And the mean difference is the mean of the sampling distribution.
When you say sampling distribution, isn't it like 1,000 things and then you take chunks of 30 randomly and then you see what the average is of and the standard deviation of all of those?
Yeah, that's a long way of saying it. That'll get you confused probably, which maybe it
I know,
did.
but the thing is, if you only have 30 data points, how can you get a sampling distribution with just 30?
Okay, so the sampling distribution is very theoretical.
Okay.
So what that means is you imagine or theorize all possible samples of 31 pairs of data. Now you have one example. That's all you got is one example. But from your one example, you can say that because your sample size is large, then that example is a pretty good predictor of the sampling distribution.
Oh, okay.
You see?
So my standard deviation for that 31 points of data is the standard error.
Right, approximately the standard error.
Okay.
And remember that the distribution we use for that would be the t distribution. And that's because the standard error is an approximation of the standard deviation of the sampling distribution, but it's not exact. And that t distribution makes that little error and it handles it. Do you see that? So yes, you don't know the exact sampling distribution, but you have a good estimate for it
Okay.
in the standard error and using the sample mean difference.
Okay.
Does that help?
Yep. I got it.
Good.
Thanks.
Are there questions? Good questions. Good questions, because they're tough stuff.
I have a question.
Mhm.
So on your post for the discussion last week,
Uh-huh.
I don't know if I missed this or what, but I don't know how did you get it's the last part that you wrote, average time it took to get down gun barrel by at least 1.65 minutes. Where did you get that 1.65 minutes?
Okay, so there's two ways. Let me give you the way that's easy to understand first, and then I'll give you the easy way to second. So the way that's easy to understand is if you take the mean for the gun barrel, and you can just drop that into the calculator to find the average, right? And then you take the mean for the other one. It was gun barrel. I forgot what the other.
No, it was skiers and snowboarders.
Oh, skiers and snowboards. Okay, so you'll take the mean for the skiers. Yeah, I was just
Yeah.
trying to remember what exactly I posted. You take
Yeah.
the mean for the skiers, okay, and you take the mean for the snowboarders, okay, and I gave you a list of data, so it's easy to find the mean, right?
Yeah.
And subtract the two. There's your difference.
Oh, okay. That's simple.
Okay. Now you want to hear the easy way to do it, because that's easy to talk about, right?
Yeah.
It's kind of a pain. You have to go to the calculator twice. But the mean difference is always the center of the confidence interval.
Oh,
So if you add the lower bound and the upper bound and divide by 2, that
Okay.
gives you, that'll give you the same value.
and it doesn't matter what the confidence interval is, 95, 90.
Doesn't matter. Yeah.
Yeah.
It's always centered at the mean difference.
Okay.
So
Oh,
that's the
yeah.
easy way, computationally wise, once you're given the confidence interval, that's the easy way. But in terms of what it means, it's better to understand that it means you subtract the two means, and that gives you the mean difference.
Okay, cool. Yeah, that's the one thing I
Yeah.
kept drawing a blank on.
Yeah, because it just kind of shows up.
Yeah,
Just some
exactly.
number
I
out
wasn't
of the
sure where you were getting that number from.
Yeah. So I promise I didn't do anything too fancy.
Yeah. And then real quickly, the other thing I keep messing up is the difference between a dependent and independent hypothesis. Like I keep messing that up. Can you just quickly?
Yeah. So one thing to want to look at is imagine, again, you have to use your imagination
Yeah.
and look at the very first item, the first number for the first data set, and look at the first number for the second data set.
Okay.
Okay. Would that be any different if you look, say, the first number of the first data set and the second number of the second data set? Is it important that they were both first? So for example, if you ask people 2 questions, things like how many jackets do you own and how many hats do you own? So the idea is when you look at the data, that first number of hats and the first number of jackets, those came from the same person.
Right. So it's dependent.
That would be dependent.
Yeah.
Okay.
So for your skiers and snowboarders example, it doesn't matter. That's why.
Right. The first skier that you asked has nothing to do with the first snowboarder that you asked.
Right. So the example that I gave was StubHub versus Ticketmaster. Those are dependent because it's the same event. Like one event is $45 on StubHub and the same event is $43 on Ticketmaster.
Right. If you're talking about the same product, they'd be dependent.
Same
I'm not
product.
sure if
Right,
you,
so-
I'm trying to remember I think you weren't clear whether it was the same product or not, but if
yeah,
the
well,
same product they're dependent,
a lot of it gets real wordy, huh? It gets,
yeah. If it's the same product, they're dependent. If it's just the first 50 things you looked at StubHub and the first 50 things you looked at, the other one you called, I don't even know what the other one is.
Okay, and then for
And that'd be independent.
Ming's post was Los Angeles versus Long Beach, and if you're going to the same destination,
That would definitely be, that would definitely be dependent.
right? Okay, that makes sense. That's a good way of looking at it.
Yeah.
And then for our project, we're buying the same product at 2 different stores, so it's dependent.
Exactly. That would definitely be dependent.
Gotcha.
And if
Okay,
you can
yeah.
do, if you can do prices at stores, I can't imagine doing it independent because
Right.
that would just get weird.
Yeah. Okay. I understand. Yeah. That cleared it up. Thank you.
Great, great, great. Other questions? These are good questions. Okay, and if not, then we'll get into the chi-square distribution. Okay, I want to let you know, by the way, one reason why I was happy to spend a long time answering questions is this is one of the easier weeks of the quarter. Okay, which means that since you got a little extra time because this is easier stuff, I recommend spending a lot of time on the project. You can get that, a lot of it done. Because so if I talk about stuff and it's not that hard, it doesn't take that long, then smile. Don't be too surprised. So I just let you know that. So first thing
will be really hard.
What's
Does
that?
this mean next week will be hard?
One more time.
Does this mean next week will be hard?
No, actually what I do, and this is my teaching style, whether you like it or not, you got to live with it, is I do a lot at the beginning and fast and furious, and then I slow down at the end.
Okay, great.
One of the reasons I do that is that if you're taking a bunch of classes, other classes tend to be really hard at the end. Like if you have an English class, that's where you have to write the big paper, so I tend to do the opposite and it seems to work a little better, So
Thank you.
Sorry if you don't like it, but that's what you got. So it gets a little easier. I mean, you still have the project. Projects are, take a lot of work, but it's no harder than project one. Okay. So let you know we have kind of a lighter week. Next week, I'm going to let you know this week is really important, especially for high level research. This is never used in day-to-day, go to the grocery store kind of thing. Yeah, you're not going to use it. You're not going to see it in the newspaper. You're only going to see it. You're only going to see this stuff in published papers. So I do want to let you know that, give you a heads up. You've probably never seen any of this before. So just let you know if you're like, oh, I've never seen this. Well, there's a reason. Whereas next week is the exact opposite. Next week is stuff you see in middle school. Okay. Now you didn't because you're too old, but the new standards and the new curriculum, they put it next week stuff into middle school. That's brand new. So if you have kids, then they're going to see it. Okay, so we're going to look at the chi-square distribution. And I want to remind you the normal distribution, I hope all of you have a good feel of the shape of the normal distribution, right? Bell curve shaped or bell shaped. You have a good shape on that. So one of the things about the normal distribution is it goes out from negative infinity to positive infinity, right? Hopefully you know that at this point, right? There's negative numbers and there's positive numbers on the normal distribution curve, right? For the x-axis. But if you square something, can you get a negative number?
No.
You can't. So in the chi-square distribution, there are no negative numbers. So I'm going to show you, and this is something I create a little visualization. It turns out there's something called degrees of freedom for it. And it has to do with kind of how many, for example, if you're asking, what is your race? Well, how many categories of race are you going to be kind of including, right? Because, for example, you could say Asian, but then you might want to say East Asian is different than South Asian or something like that. So if you have more groups, then that's going to be more degrees of freedom. So I'm going to let you know that is that the kind of more possible answers, the higher degrees of freedom you have. So you can take the slider. I'm going to do that because you're just watching me, but you can do this also in the book. And this is what it looks like with 3 degrees of freedom. And you can see, hopefully you know by now, because this happened in the second chapter, this is a skewed right unimodal distribution. Do you remember that stuff? But if you go and make the degrees of freedom higher, it kind of changes it a bit, doesn't it? Still never goes negative, stops at 0. It's still slightly skewed right, but not as skewed right. And if you go even higher, now it's starting to even look kind of normal, isn't it? So the higher degrees of freedom, the more looking like a normal curve it's going to be. But if you don't have that many degrees of freedom, then it's going to be very skewed. Any questions on the picture? Okay, just a note, unlike the normal distribution, there's only one tail. It's skewed because this thing stops at 0, which is nice because it means life is really easier in this chapter because you don't have to worry about less than, greater than, or not equal to. Does that make sense? You only have to worry about this right tail, so you don't have to, so it won't even be on the calculator which of the 3 types. There's only one type. Any questions on that? Okay, so that's a picture of the distribution. I will let you know there is an equation for this, and it is absolutely brutal. And you should smile about that, because what does that mean you're responsible for?
Calculator.
Knowing the calculator?
Yeah, you're not responsible for it all. So even Braulio hasn't seen the equation, right, Braulio? It is brutal. It's graduate level mathematics. It can't be written in like any form you've ever seen until you get into graduate school mathematics. So let you know, we're not touching the equation, but look at a picture. That's not so hard, right? That's not painful, is it? That we can see. So I want to let you know this is the chi-square distribution. There's still going to be a test statistic, which is going to be the chi-squared number. So if it was 10, it would be like right here. And it's always going to be right tail. So it'll be the p-value will be the area to the right of that value. Any questions on that? Okay, so that gives you just a visual of what's going on. Okay, really the only way of doing this stuff is, I think is by example. So I'm going to give you an example of a chi-square distribution. Okay, I somewhat made it up, although I did research and I looked up the percentages of different races in California. So here's the example I have. Maybe I'll make it a little bigger font so you can see it better. By the way, if it's ever too small font, you can always let me know and I can make it bigger. So if I don't think about it, just let me know that you want the font bigger. Okay, so example. So in California, 39% of residents are Latino. Okay, 36% are white. 15% are Asian or Pacific Islander, and 10% are other races. Okay. So is the distribution of races different for California community college students? Because one of the things we like to have at our system is we want to represent the population of California. Doesn't that sound like a good goal? Any questions on that? Okay, so it'd be good to represent the population of California because we don't want to only favor one race and say if you're a different race, you're screwed. We want to say that, hey, wherever you're coming from, you're going to be accepted just like everyone else. And that's what we want. Okay, so a survey was done. By the way, I want to let you know a survey was done, which means I totally made this up, the survey. So I did get these numbers. These are facts. The survey is just I made up. But a survey could be done of 300 California community college students. 125 were Latino. 92 were white. 33 were Asian or Pacific Islander, and 50 were other races. What could be concluded at the 5% level of significance? Any questions on the question? Any questions? Okay, so you can see this is done definitely for research. You want to find out, hey, is our community college system doing its job in making sure that we're not discriminating against one group or another group? Because that's what we want. Any questions on the idea? Okay, notice that you can't use any of the tests that we've already covered in class. Okay, there's nothing about a mean here. You can't take an average race. Does that make sense? You can't add up a Latino and a white and divide by 2. It doesn't make any sense at all. Okay, so you can't talk about a mean. This is not a yes or no question, right? The survey question is, what is your race? And you might say Caucasian. Okay, you might see Asian or whatever, Latino. So the survey question doesn't work with anything we've done yet. Do you all agree? You see how that is? So we have to do something different. And the way you handle this is the first thing, and this is something I want to give you a big warning about, is that in this chapter, H0 and H1 will be sentences. Okay. And the warning is not to make sure you make H0 and H1 sentences for this chapter. The warning is to make sure that you don't stop using symbols for the prior chapters. So if you're doing something from chapter 9 or some chapter 10, chapter 8, those need to be symbols. So, you know, like mu equals 3 or P1 is less than P2, all symbols. In this chapter, though, symbols don't work well, so we're going to use sentences. So let me write down the sentence that we're going to use for this particular one, and that is the distribution of, and maybe I'll even write racial distribution of California community college students is the same as that of California residents. Any questions on H0? I want to do the following. I want to take this word distribution and I want to put it in red. Can you tell me why I might have put that in red?
It's important.
It's important. And if you don't have the word distribution when you're doing this kind of hypothesis test, guess what's going to happen?
Points off.
Yep, you're going to lose points. It's a guarantee. And if you do have the word distribution, even if the rest is a bunch of mess, I'm still going to give you some points. So make sure that word distribution, whenever you're doing this particular type of test, that you have to have the word distribution. The good news is I'm on a computer, which means I can copy and paste. And since this is an online class, everything you do is on the computer. You can copy and paste too. But I got to change something. What do you think I got to? I'm going to add one word.
Is different.
Not.
I could do that, but that's actually more work typing wise. I'm going to add a 3-letter word.
Not.
Yep, is not the same. Different is fine, but then you have to erase is the same and turn it into different. And you could do that too. That's fine too. But not is a whole lot easier. Don't you agree? So H1 is a racial distribution of California community college students is not the same as California residents. Any questions on H0 and H1? Okay, so there's a word for this kind of test, and it's called the chi-square goodness of fit test. Okay, if you're doing it on the test, for example, if you just write GOF, I'm going to let you, that's good enough. Goodness of fit is often called GOF. Okay, but if you want to write the whole word, chi-squared goodness of fit, that's fine too. Okay, this is called the chi-squared goodness of fit test. And the idea of the chi-squared goodness of fit test is that we have a known distribution, okay? And then we have a population that we don't know about its distribution. We take the sample, from that population, and we do a test to see if our unknown population's distribution is the same as the known distribution. Any questions on what the goodness of fit test does? Any questions?
So the known distribution is the 39%, 36%, 15%, and 10%. And the
Right.
unknown is the sample that you took of the 300 California community college students. And you want to
Yep.
see if those intervals are the same as the 39, 36, 15, and 10%.
I think what you're thinking is right, but you said one little thing off. So you're right. The known distribution is these percents for California community college. The unknown distribution is the distribution of all California community college students, not the survey.
Yeah. The 125, the 92, the 33, and the 50, or
We
or
know
the
those.
population.
Right. So we know the sample, but the sample is not what we're interested in. We're interested in the population. Do you see that?
Okay.
And so the known is California. The unknown is the 2 million community college students or so that we've got. Does that make sense?
Yeah, it does.
And we know the distribution of the sample, But as we've seen throughout this whole class, is just because we know a sample doesn't mean we know the population. Is that clear?
Gotcha. Yeah.
So you use the sample to say, well, we don't know the population, but if the sample size is large enough, then if the distribution of the sample is not that close to the distribution of California, the known, then we'll reject the null hypothesis and say the distribution is different or not the same. Do you see that?
Yeah, that makes sense.
Where if the distribution of the sample is close to the distribution of California, then we're going to fail to reject our null hypothesis. And just like with all hypothesis tests, either that means that the distribution was the same, or it means that our sample size was small and we got unlucky. Does that make sense?
Yes.
Okay, so the good news is the hypothesis test idea is exactly the same as what we've been doing. Any questions on that? Okay, so it's a step-by-step process. So the first step is to write down H naught and H1. The second step, okay, and the first and second kind of go together. The second step is to decide what kind of hypothesis test to use. And for now, I'm just going to tell you as good as a fit because we have an unknown distribution, we have a known distribution, and we want to see if the unknown is the same as the known. And that's goodness of fit. I want to let you know this is one example of goodness of fit where the known distribution comes from some census bureau or something. But there's other examples of goodness fit. We have spent a lot of time in this class saying, for example, we have this, group, and does it follow a normal distribution? Well, how do you find out if something follows a normal distribution? In project 1, I just had you draw a histogram and look at it and eyeball it, but that's not a great way. That's kind of, eyeballing is not really mathematical enough. Does that make sense?
Yeah.
So instead, actually you can do goodness of fit, which we can definitely do, is to do a goodness of fit to find out if it's a normal distribution. And I'll show you how that works if we have time later. Another big distribution people look at is the uniform distribution. Because is everyone the same? All the different groups are all the same or not? And that would be uniform. So I want to give you a heads up on the types of goodness of fit tests you can have. Okay, the next step in the goodness of fit test is you draw a table, and I'm going to call it it's the observed and expected table, which I'll pop right here. And so I created a table here. We have our Latino, our white, your Asian Pacific Islanders, and your others. And then I'm going to write O for observed and E for expected. So I'm going to type in Latino, the observed. We had 125 Latinos. So 125. We had 92 whites. So I type in 92. We have Asian Pacific Islanders, there are 33. And there were 50 other. Any questions at all on coming up with the observed? I do want to let you know those are almost always easy if you're given the results of the sample. Okay, the expected takes a little bit more work, but it's not that hard. So the idea here is we surveyed 300 California community college students, right? If the distribution, so if H naught is correct, if the racial distribution of California community college students is the same as that of California residents, then we would expect that 39% of those 300 students should be Latino. Any questions on that rationale? Any questions? Okay, so what we do is we take 39% of 300, which is 117, if I did that right. Okay, you don't have to do it in your head, right? You're always allowed to use a calculator. So 39% of 300 is 117. So I'm going to put 117 in for the expected Latino count. Any questions on how I got that number 117? Okay, 36% are white. Well, 36% of 300 is 108. So 0.36 times 300 is 108. Again, you don't have to in your head like I did. You can use a calculator. Then we had 15% of our Asian Pacific Islanders. 15% of 300 is 45. And then finally, 10% are other races. 10% of 300, you might be able to do that one in your head. That's 30. So let me ask you, are there any questions on how I came up with this table? Okay, so now that we have the table, now we have kind of like the data. We know what test to use. What's the next step? You should be used to it by now.
Calculator.
Calculator. And by the way, this is one that you would use a 0.05 level of significance. How come?
Doesn't make a difference between type 1 and type 2 error.
Yeah, and in particular, this is social science. Do you agree? This is sociology. Sociology always uses 5%. It's just like, I don't think I've ever seen anything in sociology that wasn't 5%. Just let you know that. So I'm going to use 5% since this is sociology. Okay, so now I need to go to my calculator. I tried to make it easy. Which calculator do you think we're going to use? What number?
21.
21, good as a fit. Okay, and by the way, you might smile about this. We're doing good as a fit test for independence and homogeneity. We're almost done with this class. Next week, we'll do regression analysis, and the week after is ANOVA. And that's it. That's the whole class.
Oh, no.
So what's that?
I said, oh, no.
Yeah, so we don't have much left. We're almost done. Okay, so I'm going to click goodness of fit. And it says type in the values from the observed and expected separated by commas. Okay, so I'm going to go in here and I can copy and paste, but I won't put the commas in. So I'm going to copy the observes in. Now put commas in. That wasn't too hard, was it? I can copy the expecteds. I can paste that in. And then put in commas. And you notice there's nothing else to do. Okay, you don't have to deal with left, right, tail, two tail, that kind of stuff. There's no confidence interval with this. It just doesn't happen. So hopefully you're starting to agree that my promise that this is a little bit easier than what we've done is right. So hit calculate. Okay, so we see that the chi-squared test statistic is 19.45. So let's write that down. So chi-squared is equal to 19.45. If you want to write CHI and then with the 2, that's fine too, because it's kind of hard to find this capital chi letter. The p-value is 0.0002. Any questions on the chi-squared and the p-value, the chi-squared test statistic and the p-value?
Can you just remind me again what exactly the test statistic represents?
Okay, so let me show you. That's why I did this picture. So our test statistic was 19.45. Okay, our degrees of freedom turns out to be 3 on this one. So just trust me on that. So if I go to 3 degrees of freedom and I go 19.5 or so, that's right here. Do you see that on the picture?
Yes.
So the test statistic is that placement on the curve. And you could see that the area to the right of that is almost nothing. Almost everything is to the left. Do you see that?
Yes.
And that's why the p-value is so small. Because there's almost no area to the right.
Okay.
Okay, so that's what's going on. Does that make some sense?
Yeah,
No,
I mean, I don't have a like understanding of it, but I understand what you're saying.
Yeah, the mathematics behind it is way too brutal for this class. You would have to change your major and then go to graduate school, and then you can get the mathematics. So I'm not even going to attempt to do the math for you if you're okay with that.
okay, but can you just tell us in what context the test statistics is asked for?
It's the mathematics behind what's going on. It's the little tiny piece I can ask because there's not much to do there.
Okay.
And it allows you to look at a curve and kind of like when you did the normal distribution, if it was far left or far right, you can look at a picture and can see there's not much area. It's the same thing, but now it's not the same shape, but it's this far right in this case doesn't have any significant area. Do you see that?
Yeah, so is it kind of like saying this is the end of the curve?
Yeah, it's the end of the curve where anything really happens.
Okay, I got it.
The curve goes forever, but it just never happens. Does that make sense?
Yeah.
Yeah.
And one more time, the degree of freedom represents what?
The degrees of freedom turns out is one less than the number of items you have. So we have Latino, white, Asian, other. There are 4 of them. Degrees of freedom is 3.
So it's always that? It's always one less than
Yes, it is for goodness of fit.
groups minus 1. Okay.
Yeah. Yep. So the idea, a lot of degrees of freedom means there's a lot of different answers to the survey question.
Gotcha.
Whereas a smaller number of degrees of freedom is not that many answers.
Is there something on project 2, I forget, where we have to explain the relevance of the T statistic or the...
Yeah, so the T statistic, the test statistic, because T and Z are basically the same, are almost the same when it comes to a large sample size, which you're required to have over 30, then the T is like the Z-score.
Oh, okay.
And that tells you how rare something is.
Okay.
Does that make sense?
Yeah.
And you could say the same thing with the chi-squared, but it's a little more complicated, so I decided not to get into it too much. So I just showed you.
So all we need to know for that is it's basically the end of relevant.
Yeah. Whereas if the test statistic was 2, then there's a lot of possibility it could be to the left. You see that? To the right, I mean.
Yes.
Right? But a test statistic of 19, there's almost no possibility to the right. Okay, good questions, really good questions. All right, so now it's time to state the conclusion. So here's the first part, which you should all know. What's the first words?
There is.
Yeah, there is. And I'm going to write p-value is very small. And remember, our definition of very small is less than 0.01. So then I'm going to put strong. Statistically significant evidence to conclude that, and now the good news is I'm on a computer. I can copy and paste H1. Copy. Paste. And then make that T a lowercase. That the racial distribution of California community college students is not the same as that of California residents. Any questions on that? Okay, I want to let you know something. We're able to say that the distribution is not the same based on this survey, right? Does this tell you, based on what we just did, which is the one that is like way off? Latino, white, Asian, or other? Do we get that out of what we just did?
No.
The answer is definitely not. Okay, so the only thing you can get from a chi-squared goodness of fit test is that the distribution is different. It doesn't tell you the details of how it's different. Is that clear? Okay, and this is day 1. of what I'm going to tell you, and I'm going to tell you this over and over again. Do you think there is a way to find out how it's different?
Yeah.
Yeah.
Yeah. And this is day one of what I'm about to tell you. To find out how it's different, any guess on what you're going to have to do?
Use
Another
a
hypothesis
calculator.
test.
No,
Look at a graph.
no, you're gonna laugh when I tell you.
Level math class.
There we go. It doesn't have to be graduate level math, but it has to be upper division. And it might be a psychology class, actually. You know, it might be a psychology class on advanced statistics. Does that make sense?
Yeah, this might be a silly question, but I mean, you can't just look at which one had the biggest difference. Like other had a difference of 20 and
Yeah,
No,
but you have like 100 degrees of freedom. That would be crazy.
You have to do more sophisticated tests. And I'm going to stop there because I can't get into it. But if you really want to know, then you got to take more statistics. Take another stats class. And, you know, it's not because I'm lazy. It's just because this is a lower division stats class. It's called elementary statistics. So I want to let you know that a lot of times we can't do everything. And that's just because this is a community college class. It's lower division. Okay. Or if it was a university in freshman year or sophomore year, same thing. Okay. But there are ways of doing this, but you need to take more advanced stats. Okay. Sound good? Okay. It doesn't have to be a higher math major class. That is understanding the chi-squared shape of curve and formula. That's mathematics. Okay. So I want to let you know that all we're going to be able to say is the distribution is not the same. Any questions on that? By the way, if the p-value had been, let's say it had been 0.37, what would the conclusion be? How would it change?
there is insignificant evidence.
Yeah. So there is insignificant evidence or statistically insignificant evidence. And I like to say to make a conclusion whether or not the racial distribution of California community college students is not the same as that of California residents. I tend to word it a little bit differently, but basically that's the other choice. And that can happen sometimes. All right, so now comes the next question. Does it matter what season a person was born when it comes to the type of car they drive? Okay. The table below shows the season and car type. Okay, so this is very different than what we just did. We've never done one like this either. What can you say about the survey? If you were to run the survey, ask people, and what would you ask?
When were you born and what kind of car do you drive?
Exactly. There's two questions. And notice the answer to both of these questions is qualitative. Any questions on that? So for example, I was born in the summer. And I guess technically I drive other. Do you know what that means? Do you know what it is for me? I think I've told you guys, no? You know what my other is?
Hummer.
No, maybe I haven't told you. If I haven't told you, you'll never guess.
Tesla.
No. Now you guess.
Rivian.
No. Should I tell you?
Subaru?
No.
Volkswagen Beetle.
You're not going to guess.
You walk everywhere.
There you go. I don't have a car.
What? Really?
Yeah, it's my little experiment for the last 6 months. Just for fun.
That's pretty cool, man.
Yeah, so it's new. So I'm an other, but notice I'm not a 33. I'm other. Does that make sense? And these numbers, like this 81, that doesn't mean someone said 81. That means there were 81 people who answered they were born in summer and they drive a sedan. Does that make sense?
Yes.
So these are counts. Okay, these aren't answers to the survey question. These are how many answered in this combination of category. Any questions on that? Okay, so this is not good as a fit, right? We're not seeing if one distribution fits another distribution, are we? We're just want to say, does it If someone tells you they're born in summer, does that give you a better idea of what kind of car they drive? Is that clear? Or if someone says that they drive an SUV, do you have a better guess on when their birthday is?
It's almost like, is there a correlation between the when you were born and the type of car you drive?
Right, but I want to be very careful. Next week, we're going to talk about correlation. So I want to specifically avoid that word. Instead, we're going to say, are the type of car you drive and the season you were born in independent or dependent? Does that make sense?
Okay.
Correlation is going to have a different meaning, and we're going to get there next week, I promise. Okay, so we're going to use what's called a chi-squared test for independence. So that's our next type of test that we have. And it's used when we have two survey questions that are both qualitative, and we want to see if they're both independent, I didn't write this down, or dependent. Any questions on the idea of a chi-squared test for independence? Okay, so now once we've decided that, we need to write down H naught and H1. And as I mentioned, this week is going to be all sentences. So H naught is, we can say, the season a person was born in, and the type of car they drive, are independent. And what I want to do is I want to put that word independent in red. Why am I putting that word in red?
Because it's important.
Yeah, because if it's not there, you lose points. Got it?
So is H not always the independent one?
Yes. Yeah, good question. And the answer is always yes. Yeah, you can't really show that they are independent. You can only show they're not independent. It's one of those things, just like you can't show two things are equal, right? All you can do is show they're not equal, or one's greater than the other. So for H1, all I have to do, copy and paste H naught. And here's the hint. I'm going to erase two letters.
In,
exactly. And erase the letters I and N. It's very easy computer-wise, isn't it? And the season a person was born in and the type of car they drive are dependent. And I'm going to keep that in red because that needs to be there. Just to let you know, if you switch independent and dependent, that's like the worst mistake you can ever make. Because then you're going to end up with the exact opposite, the exactly wrong answer. Does that make sense?
yeah.
And you don't want that. That's like the worst mistake you can make in the real world, is to switch those two. Any questions on this? Okay. So again, what I'm not telling you at all is why the chi-squared is the right, shape of distribution to use. The math is way too hard for that. But can you trust me?
Yes.
Yeah, so we're going to use the chi-squared distribution, and we're going to go to the calculator. So let's go back to the calculator menu. And my guess is you should all have no problem telling me which test to use, which number.
22.
Yep, 22. Again, I tried to do this in order. So test for independence. This one's different because here we truly have a table. Before we had a table, but now we have multiple rows and multiple columns. So now I just did A, B, C, D, etc. First, second, third, fourth, fifth. By the way, if you need more than what I have here, then this won't work. This calculator won't work. Any guess on what you can do that we've already gotten into once or twice actually now instead of this calculator?
The spreadsheet?
Yeah, the spreadsheet. Spreadsheet has everything, and the spreadsheet allows you to do as many columns and rows as you want. So I'm going to go and pop in my numbers. We have 73, 81, 76, 7. Let's see, 73 and 81. I'll do two at a time. 73, 81, 76, 78. 65, 68. Easy to make a mistake in typing here. 62, 64. 43, 51. 48, 50. Okay. Just let you know, just like before, when we had an observed and an expected, the chi-squared kind of was a determination of how far the observed is from the expected. It turns out there's an observed and expected here also. This is going to be this is a question I don't expect any of you to remember, but you might. maybe it'll happen. When have we seen something like that where you can get the expected?
On the expected value calculator.
The expected value calculator, that's a good guess because I have the same word, but no.
Frequency table?
Frequency table, nope. Good guess again, but it wasn't right. Okay, I think I'll tell you. Do you remember we had a independence in chapter 3 to see if two things were independent of each other when we looked at probabilities? You may not remember, but it happened, I promise. So in chapter 3, I asked you, are these things independent? And you had to figure that out by doing a calculation. Do you remember something like that? Vaguely?
Yeah.
So it turns out that that calculation will give you the expected number for each of these table values. And if those expected numbers are very far from the values, chi-squared, the test statistic is big. And if they're very small from those values, if they're real close to the values, then the test statistic will be small. So I'm just going to let you know that that's what's going on here. Most of the time, you're just going to be popping in and hit calculate, but I want to let you know what's going on. And that's what's going on. Okay, so now I'm going to hit calculate. There's our chi-squared, 0.48. And then our p-value was 0.998. All right, what do you notice about this p-value?
Very high.
Yeah, this is as high as you've probably ever seen a p-value. Okay, so what does that tell you?
There does not appear to be a correlation. There's
Yeah, but remember, we don't use correlation. Don't use
They
the
are
word correlation.
independent.
Yeah, it means you can't say they're independent.
There is not
But-
enough evidence to, there is
They're
data.
not dependent.
Yeah, so we don't, we have insufficient evidence. So there is insufficient evidence to conclude that, and now all I do is copy and paste. The season a person was born in and the type of car they drive are dependent. And not only that, it is so close to 1, you wouldn't even think about having a bigger sample size because hopefully maybe you'll show they're dependent. Good luck. Does that make sense?
Can you just remind me one more time of when you would want a bigger sample size? If it was like 0.06,
Yeah, 0.06, you'd cry. Because that means that,
so close.
you thought you were right, but you're not able to show it, but you're so close. And you can't use the same sample size. Because if you use the same sample size over and over again, eventually, if you're wrong, eventually you're going to have a type 1 error and show you're right, even though you're wrong, and that's bad. Do you agree?
Right. So at what number does it become like 0.078?
There isn't like some kind of line at which you have to go by. Does that make
Okay.
sense?
Yeah.
But 0.06 is definitely close to 0.05. 0.998, that's like, forget it. Don't even think about doing another study with this because it's hopeless. Got it?
Yeah.
Okay. So that's kind of the idea. When you do your project, you're gonna have to analyze that. Okay. So do you remember the law of large numbers? Again, it came a long time ago. It says that if your sample size is large enough, that you're very likely to get something close to your population.
Right. Okay.
That's the law of large numbers. Okay. So when you have 0.998, that pretty much convinces you that we have large enough numbers and that our standard error is small enough. I mean, does that make sense?
Yes.
Whereas if you had 0.06, you'd say my standard error is too big. So I need a bigger sample size. So I can let the large numbers tell the truth.
Okay.
Does that make sense? Yeah.
Yep.
So, and that'll be important on, again, when I said you have to tie things into your standard error, that's how you tie it into your standard error on the project.
Yeah, that's good to know.
Yeah. So that's why I'm repeating it a few times, because it's an important one for the project. And it's one of the hardest parts of the project is to incorporate the standard error everywhere. Okay. Whereas for the confidence interval, if your 95% confidence interval is useless, or even 90% is useless because it's way too wide, your standard error is too small. I mean, too big, sorry. Standard error is too big.
In that case, would we go back to more data?
Here's what you would do. In your paper, you would say that because the standard error is too large, we recommend doing another study with more data. Don't go do another study. Does that make sense?
Yeah.
Yeah, I got it.
Yeah. So that's a recommend. You make recommendations, okay, to the client. You say, hey, client, you need to pay us more so we can actually do more, a bigger study. Is that clear? Okay, so there's our conclusion. Okay, let's do another one. Okay, do single men and women take the same type of vacation? What do you think?
No.
Okay, we'll find out. The table below shows the results of a study. Okay, so we have male and female, and the types of vacation I'm going to call international, out of state, and more local. Does that make sense? Okay, and I want to let you know I totally made up these numbers, but you can imagine a study being done, right? You could do a sample, and you could do a survey and ask a bunch of men and a bunch of women, what type of vacation did you take last, international, out of state, or more local? Is that clear? All right, so notice that, again, we're in a case where the answer to the survey question is qualitative. It's not a number, right? What type, any guess on what type I tend to take? What type of vacation?
Local.
Local.
More local. Yeah, I'm going to call it more local because of where I live. Sometimes out of state, but I don't really call it like far out of state because I can walk to Nevada from my house. But so I'm going to call it more local. Does that make sense? But whatever you might say international, you like to go out and, explore the world or something. We all have different, ways of doing things. But what about men versus women? Okay, notice this is different. This is not a goodness of fit test. Why is this not a goodness of fit test?
Because there's no known.
Right. We're comparing the distribution of men and the distribution of women, right? But we don't know the men and we don't know the women. Is that clear?
Right. So if we knew the men and we wanted to compare the female to the men, it would be goodness of fit.
Exactly. Exactly. This is not a test for independence because we're not asked to see are they dependent or independent. We want to find out if the distributions are the same. Do you see how that works?
Yeah. And how would you word that to make it dependent or independent question? Does your gender depend?
Yeah, or you'd probably go the other way because you don't change. Well, I guess nowadays people can change gender, but most people say, base your gender might,
So it'd be like,
tell you about what kind of vacation you make.
right. Does where you go on vacation determine your gender or something like that?
Yeah, where you go on vacation, not determined, but maybe related to.
Right. I get it.
Yeah. Okay. So this is called a chi-squared test for homogeneity. And that's what we're going to be using. It's called a chi-squared test for homogeneity. You've heard the word homogeneous before, right? Where have you heard that?
Milk.
Yeah, homogeneated. Okay. Do you know what that means? You know what it means? That
It's like uniformly spread out.
Together or something?
yeah. I guess if you milk, and I'm not a farmer, by the way, but I guess if you milk a cow, it's like different parts of it in different places. And you need to mix it to make it taste like milk. That's what I've heard. I don't know this for sure, but that's what I've heard. And homogeneity means it's all mixed up. Does that make sense? And not separated from each other. So in other words, men, women, they're all together. It doesn't really matter whether you're a man or a woman when it comes to, right? Men and women have the same distribution. Does that make sense? So this one comes up in a lot of places where, it could be men versus women, or it could be one method of doing something versus another method of doing something. And what are the results? Does that make sense? So there's all kinds of different homogeneity tests that can happen. All right, so our H naught is going to be the following. The distributions of vacation type are the same for men and women. Any questions on H0? Okay, for H1, I'm going to do what I've been doing. I'm going to copy and paste. And I got to add in a word. What am I going to add in?
Not.
Not.
Not. Exactly. So the distributions of vacation type are not the same for men and women. Any questions on that? By the way, are you in agreement that this is one of the easier chapters so far?
Oh yeah, it's way less wordy.
Yeah, most people really love this chapter because it's like a relief. Okay. And again, chi-square test for homogeneity. I guess I can't hurt to put it twice because it's the big test for this one. Okay. So also on this one, I'm going to go to the calculator. Let's go back to the calculator, Manny. And you better be able to tell me which one I need to use.
23.
Yeah, 23, test for homogeneity. And here, A and B. A are going to be the men, B are going to be the women. So 29, 47, 33. And then 38, 42, 36. Any questions on that? Then I go and hit calculate. What do you see?
High p-value.
Yeah, high p-value, and chi-squared is 1.40. The this actually has 2 degrees of freedom. So if I go to 2 degrees of freedom just for fun, and if you look at 1.4, that's like over here somewhere. There's a whole lot of area to the right of that. Do you agree?
Yeah.
That's why the p-value is that area. So they are very related, the test statistic and that p-value. So again, chi-squared was, where was it?
Oh, because that other example you did with that, the p-value was super low, right? And then
Right, and that's because we were far to the right.
yeah, and the test statistic pushed you way out. Far to the right.
Yeah.
Okay.
So chi-squared is 1.4, about. And the p-value was 0.5. And notice 0.5 is not the same thing as 0.05. So always pay attention to the decimal. Any questions on that? So the nice thing is the conclusion's easy now. We know the first few words, which are?
There is
Keep going.
Insufficient evidence.
Do
Two.
you have to put statistically insufficient for these? Because I
Yeah, you
noticed in
should.
the last example that you didn't.
Statistically insufficient. Typically, if you write insufficient, then that has that in. If you do insignificant, for some reason, they put statistically insignificant is standard.
Okay.
Yeah, sorry about the, it's called English. The funny thing, I'm a math major, so I don't have to deal with that stuff, and then I have to deal with it once in a while. But not as much as, say, an English major, right? So there's insufficient evidence to make a conclusion about whether, and then I copy and paste. The distributions of vacation type are not the same for men and women.
So is that always the case as the test statistic goes up, the p-value goes down?
For the chi-squared, yes. For the t, it's true if the test statistic is positive. And if you have a right-tailed test, right? So that's always true for a right-tailed test. And this chapter only has right-tailed tests. Does that make sense?
Yep.
Whereas for a left-tailed test, it's the exact opposite.
Can you explain what the chi-square is again?
Chi-squared is, the math is too hard, but it's a number that represents how far the observed is from the expected.
Oh, so it's kind of like a standard deviation?
No, it's more like a z-score.
Okay.
It's how unusual it is. And the idea is that if H naught were true, then men and women would be the same. Does that make sense?
Okay.
And then you could look at the proportion of the whole population that's international. Is that clear?
Okay.
Well, then we could say, what about the proportion of males who are international? Is that close to what we expected if men and women are the same and we looked at the whole proportion? Do you see that?
Yeah.
And then we could do the same in out of state and the same in more local. And the chi-squared is kind of it kind of puts them all together.
Is it so that the higher the chi-square score, the more unlikely it is to get this thing if the null hypothesis were true?
Yeah, exactly. Yeah, very similar to what we've done before. Okay, any questions, any more questions on this before we get to another example? Oops, I want to change this. Okay, so the next question is, a study was done asking how far they traveled on Memorial Day weekend. Okay, the mean was found to be 120 miles and the standard deviation was 40 miles. Sound good? Table shows the results. Okay, and actually I want to Don't want to put that in yet. So they did a survey and 56 people traveled less than 80. 61 traveled between 80 and 160, and 12 traveled between greater than 160. And the question is the distribution normal? Any questions on the question? What type of test do you think we're going to use here?
Goodness of fit.
Yeah, this goodness of fit. Because the normal distribution, we know the normal distribution, right? You could draw a picture of it. We know everything about the normal distribution. So the question is this unknown distribution, which is the distribution of how far people travel, is that the same? Does that fit the normal distribution? Any questions on that idea? All right, so I wrote down the observed. How do we find the expecteds? I wrote the observed already. How do we find the expecteds? How many would we expect to be less than 80?
Well, a normal distribution is symmetrical. So you try to find the middle point first, right?
Okay. Well, the middle point is 120.
So you take standard deviations away from 120.
Yeah, and by the way, 80 is not some random number I chose. It's very important. How come?
It's one standard deviation away from
Exactly.
20.
Exactly. So it's one standard deviation below the mean. And in fact, how about 160?
One above.
Standard. It's it's one above it.
It's one above it. So in between 80 and 160, what percent should there be?
95.
No, that was two standard deviations.
60 something.
60 something. And remember?
68%?
Yeah, 68%. And I'm putting this in. This is not going to be the expected number, but I'm just putting it into, so we have it there. Got it? So we expect 68% to be between 80 and 160. Is that clear?
Yeah.
Now we have symmetry. So if 68% is in between these, 32% is outside. Is that clear?
Okay.
How much is to the left?
32 divided by 2.
What's 32 divided by 2?
16.
Yep, 16%. And by symmetry, how much should be the right?
16%.
16%. Symmetry is wonderful, isn't it? Any questions so far? Okay, notice that our sample size that was equal to 56 plus 61 plus 12. Any questions on that? Okay, so that is what? 56 and 61 is 117 and 12 is 129. Sound good? You should always check when I do it in my head, but I think that's right. Okay, so there's our sample size. So now to find the expected number that are less than 80, we take 16% of 129. Any questions on that? So I'm going to go for the old Google. 0.16 times 129. And I'm going to round to the nearest whole number, call it 21. And 21 greater than 160 for the same reason. And 68% we're supposed to be in between. And that was 88. Any questions at all on how I got the expecteds? Okay. So I need to write down my null and alternative hypotheses. And it's pretty easy. I say that the distribution, remember it has to have the word distribution when you have a goodness of fit, of miles driven or miles traveled on Memorial Day weekend, 1L. Is, any guess?
Normal.
Normal. So H1, very simple. What do I change?
Not normal.
Yep. Any questions on that? Notice this is goodness of fit. And you will be asked for the name of the test, by the way. Okay, so make sure you get these names down. So we need to find the test statistic and p-value. So now we just go to the goodness of fit calculator. Piece of cake. We have our observed, our 56, 61, 12. Our expected, 21, 88, 21. And we calculate. Okay. Chi-squared is about 70. What's the p-value?
Really high. 4.
Can the
Really,
p-value be 4 point something?
Oh no, there's the E negative 16 there.
Right. I put this on purpose. I want to always remind you, don't ever forget to look to the right-hand side of the number to see if there's some scientific notation stuff.
So it's really low.
It's really, really, really low. It's not zero, by the way. The p-value is never zero, but it's really, really low. So instead of equal, I'm just going to write less than 0. Throw some zeros in and put a 1. Let's think I put O's. Let's try again. There we go. As many zeros as you want, basically. Any questions on that? So this is about as strong statistically significant evidence as it gets. So what does that tell us?
that it does follow the normal, it does not follow the normal distribution.
There is extremely strong, keep going,
Statistical evidence.
significant evidence that the distribution of miles traveled on Memorial Day weekend is not normal.
Yep. And I'm going to copy and paste because it's a lot faster. Any questions on this? Any questions? So just to let you know, we just tested for normality. You can always use the chi-square test for normality. I will let you know that there is a more sophisticated test for normality that kind of puts this together with a much higher strain. But we're not going to do that in this class because you have to take a upper division statistics class to truly get a much better test. Because here we just kind of randomly picked one standard deviation, right? Why not two? Does that make sense?
Yeah.
So I'll let you know there are more sophisticated tests that deal with that. But the chi-squared will test. It does work. But there's more sophisticated chi-squared kind of test. So I don't have time to do one, but again, the other main type of goodness of fit test would be to see if you have a uniform distribution. Okay. And typically it would be things like something I did when I think I told you my old story that I used to be a card counter. Did I tell you that? I think I told
saw
you.
At a casino?
I saw it in
Yeah.
one of the videos.
Yeah, I was a card counter at the casinos. And in the old days, nowadays it's a big corporation that does the casinos. Do you know who ran the casinos when I was playing, when I was 21?
The mob?
Yeah, the mob, the mafia played. And what they do is they would, when they saw someone who was counting cards, they would bring in a cheater.
Really?
Oh yeah, yeah, yeah. And I tell you, my grandfather told me all about it. He was in Vegas, and I think I won't tell you all the details, but you get the idea. But they bring in a cheater. So I would have to not just count cards, but I would run a chi-squared test to see if the distribution of cards was uniform.
You'd
Does that
have
make
to
sense?
memorize all the hands then, pretty much.
Oh yeah. I have to watch every card that went by, and I did a chi-squared test in my head to see if they were cheating or not, because they would literally bring in a magician, someone who can, put whatever cards they feel like on their side. Does that make sense? And if the chi-squared test statistic was too high and the p-value was low enough, do you know what I did?
You would like leave the
Went to a
table?
different casino.
I left the table. Yeah, you can. By the way, you don't say anything. You
How
say
many
something.
hands did you have to watch before you could run that?
Pretty many, actually. Pretty many.
You have to lose a lot of hands before you left.
Yeah, but I got good at it. Yeah, so it's detailed. But the point is that was one experience I had of doing a chi-squared test for a goodness of fit test, checking to see if there was a uniform distribution. Does that make sense?
You can't even do that anymore though, right? Because they don't play through the whole deck. So isn't counting cards kind of like doesn't
Right.
work?
So I'll let you know that when I
Like
moved
work
to
anymore.
Tahoe, they hired me to help them change the rules like what you're talking about. So I made money on both sides.
Or they play like multi-card decks.
Yep, that was all part of what they hired me for. Because
Would
when
this work on
the
video?
corporations took over, they couldn't bring in their, killers. Yeah, so they needed mathematicians actually. So let you know, that's real world stuff. It happened to me. So anyway, so if you lose now, it's my fault because I made sure that everyone loses. But we're about done. That's those are the main tests. We've had good as a fit. We have a test for homogeneity. We had good as a fit, independence, and test for homogeneity. The hardest part about this, any guess?
Knowing which test to use?
Good. Yeah, it's exactly the hardest part is which test to use. Once you know which test to use, you just follow the procedure and you do it. It's no big deal. But which test to use could be kind of a pain. You have to kind of really read through it. So I think I'm going to stop the recording.
I have more questions about Project 2.
And the secret word for this webinar is distribution. Because when you're doing a goodness of fit test, you want to find out if the distribution that is unknown, or the distribution of the unknown population, fits the known distribution. So distribution for the secret word.